All right, so questions.
What the hell is sugar? Are you doing diet?
No, it's zero sugar. Oh.
Please don't die, dude.
Sorry, Nick.
Did you go into a coma? I'm calling 911.
I'm calling 911.
All right, so let's talk about ODP 419. Let's talk about ODP 420. I think that's the last ODP for the week. Is the one that was posted today. So 419, this put get business. All right, so this is kind of like the snippet of code that we looked at yesterday and developed with some more details added to it. Basically, you have a global variable for saving this value in. Your put function takes an argument and just puts it in that global variable, and your get function just reads from that global variable and returns it. But there's lots of ways you can go wrong with this. For example, if you say this, right, this will no longer work. Because as soon as you say int saveval inside a function, that variable saveval is local to that function. And so when I set saveval equal to I, it's no longer this saveval up here.
Right.
It's this saveval here. When I return saveval down here, it's this global one, which is still equal to 0. So putting this up here will do me wrong. And if I do this, same thing, int saveval while I'm returning the value of a local variable. And even if I try to do something like this, right, this is just setting saveval, the local variable, equal to saveval, the local variable. It's not even seeing that global saveval.
So if you didn't have the saveval in the first put function, right, would it call the global variable in the get function?
Say that again, or differently?
Like if you didn't, like, I don't know, if you had saveval just in the global and in the get function, would it return the saveval from the global?
If I understand you, yes.
Okay. How can you call a local function from a local value like saveval from a different function?
You can't. That's what it means to be local.
Oh, okay.
Right? It means it only exists within the scope of that function. Once that function exits, that variable's gone.
Okay, so try to keep things global as you can if you want to call it like it.
Yeah, but be really careful with globals because they're really easy to misuse.
Okay.
Here we definitely want a function to save a value that we're going to try to access outside that function. That's why we need a global. But in general, you know, typically your main program has the variables that you actually care about. And if a function wants to use those, what do? You pass it as an argument so that the function has access to it. If you make global variables, especially inside main, it's really, really error prone. Because things will think they're using a global and not be doing it, or they'll think they're using a local and they'll actually be using the global, and it's generally frowned upon. But this is kind of an exceptional case where you actually do need something that exists outside of the function. But usually pass things through arguments, keep them local.
Yo.
All right, so 420 is almost exactly like 419, except you can save up to 10 different values with your put function, and you can retrieve one of 10 different values with your get function. So put now takes 2 arguments. The first argument is like a memory register number on your calculator. We can save something in memory 2 or memory 5 or memory 7. So we can say put, the first number is something between 0 and 9, which is where we want to put this value, and the second number is the value we want to save. And then get, we tell it which memory we want to get from, memory 0 through 9. So it takes one integer, which is the memory number, and it returns the value stored in that variable. So here's some sample code that uses this fancier put get function. For example, I'm putting 55 into memory location 5. I'm putting 111 into location 1. I'm putting 13760 into memory location 9. And then when I say get, I've got a loop here which says get memory location 0 through 9 inclusive. And I haven't put anything in memory location 3, for example, so whatever I get when I say get 3 is kind of unpredictable. And I'm not going to ask you to deal with that case. You can assume if someone's getting memory location I that somebody's already put something in memory location I. So don't worry about that. But we can run this test code anyway. Put get, not get put. Right, and it does the right thing. Memory locations 1, 5, and 9 contain the things that I put in them. And it just happens that the other ones have zeros in them.
I feel like we're building an Excel spreadsheet.
Yeah, kind of.
I don't like it.
You do or don't.
Okay, I don't.
So this is a small change on 419. Basically, instead of having a single integer that we store our values into, you need an array of integers. And you got to be able to store 10 things, so it's an integer say val bracket 10, and put should store something in an element of this say val array, and get should read an element from this say val array. So it's a relatively minor modification to what we already have here. All right, so any questions, worries about that? Yeah.
I already finished this one, but I was just wondering, is there, like, would you ever want to make the index global too? Would that make things different for processing? Because then you wouldn't have to have get receive index either.
Yeah, but how would you tell get what to get? You need something which
I
says
guess you could have
set index or something.
Yeah.
So that could be useful. I mean, you could say set index 5, and then put could just take a number and put it in 5, and get could read from 5.
Yeah.
And yeah, if you wanted to do something like that, that would be another global variable. Be perfect use for it.
So, are we talking about like that's the actual number of the memory address on the computer, or
No.
are we talking just like a place in an array that we create?
Yeah, it's kind of like it's kind of like when you have a calculator. So here's my free calculator program, right? So I have some value and I want to store it. I can say store, and it gives me a list of 9 locations I can store it in, right? So I can store that in memory location 6. And then when I want to recall, I can say what should I recall from. So it's just an index from 0 through 9. But it would be interesting to make it an actual memory location. That would be cool.
Man, I really got sprint.
Yeah, I did that on purpose. All right, so let's go back to super duper get car. So, which I just undid what we did in the last class. So, prototype for the function. Our main program just calls super duper get car, and as long as it's not end of file, it prints out the character that it returns as a %C and so on. And we left our get car function as follows: get a character. If it's end of file, return EOF. Otherwise, convert it to uppercase, and if it's a space, change it to a space. And so I have a test file here with some upper and lowercase stuff and some spaces and new lines. And if I run that through my Go file, everything comes out uppercase. The new lines got changed to spaces, the spaces stayed spaces, and so on and so forth. So there's one more requirement. Alright, so convert everything to uppercase. We're doing that with 2-upper. Convert new lines and other white space into spaces. So we're doing that with is space. And then the other thing was ignore the following characters, parentheses, quotes, and dashes. And right now, you know, parentheses, dashes, quotes are coming through in my output. So let's embellish this function. So we call getCar, we save that into this integer C. And let's do a check and see if C is one of these characters, a quote, a double quote, parentheses, or a dash. And if it's not, then we're just going to go on with our normal stuff. Is it end of file? If it is, return end of file. If it's not, is it a space? And if it is, change C to a space. And then change C to an uppercase. And then return C. So this was what we had before yesterday, right? Get a character. If it's an end of file, just return EOF. If it's not an end of file, is it a space? If it is, change it to a single blank. If it's not, convert it to an uppercase letter, and then just return C. So let's add in this last piece, which is check to see if C is one of these special characters we should ignore. If it's not, business as usual. What should we do if it is a character that we're not supposed to read? How do we skip it?
Increment at least, so in my code, I have an array of different characters for the phrase, and just move on to the next character.
That's not ignoring it though, right? Our goal is when we read our input file and we print it out, we should never see the quotes, we should never see the parentheses, we should never see the dashes. Right? They should be completely stripped out.
Oh, I do want to point out, like, I'm skipping it, but then like I have two different indexes, and one's tracking like what's actually going to be in the phrase, and then one's just like each character.
So you're skipping it on the input?
So I'm skipping it on the input part, but the output part is staying where it's at.
Okay, is your input saved in an array?
I think.
Okay, because I was suggesting reading input one character at a time rather than saving it.
Okay.
Just to deal with long lines. Yeah.
Just help me skip the ignorable characters when you just call getCar again.
Yeah. So let's just come back up here. Go back to getCar. You've done this, you know, several times already. You did this in your stick picking game. Ask the user to enter a 1, a 2, or a 3. If they don't enter a 1, or a 2, or a 3, what do? Go back up and ask them again. Enter a 1, or a 2, or a 3. Right? So anytime that we're doing error checking, we do this kind of loop. So we can do this here also. get a character. If it's a character that we're not interested in, get another character. If it's a character we're not interested in, get another character. And so this will keep looping as long as we're ingesting quotes, parentheses, or dashes until we read something that's not a quote, parentheses, or dash, and then we just go on and we do our regular code that we were doing yesterday. So let's write that up. So super duper get car, read one character. Should we ignore this? And I can't just put a single quote inside single quotes because the compiler is going to get confused. Because quote, quote next to each other means an empty character. And so this looks like quote, quote followed by the start of another character. So there's a trick we do in C. We use this backslash. Backslash quote means this is just the character quote. It's not the end of my it's not a closing quote. It's just a character. Right, so this is a character of a single quote contained inside single quotes. So that's the character, single quote. So if C is equal to one of these characters that we should ignore, let's call getCar again. So that's a loop that keeps skipping over characters we want to skip. So now it's a character that we actually care about. And we can check for end of file, we can convert it to uppercase, we can check to see if it's a space, and change it to a blank if it is. And then we just return C. So if we run that, now our output looks like it did last time, except the quotes, double, single, parentheses have all been removed. Right, so if I write this code with getCar, right, it just reads my file and faithfully reproduces it. If we do super duper getCar, it does those three things we wanted to do in the beginning of PA4. Uppercase, dealing with spaces, getting rid of special characters. Yeah?
So are we assuming that it's only going to contain those special characters, like no curly brackets or anything?
Curly brackets, just eat them as curly brackets.
Okay.
Backslashes, everything else, yeah. Because mostly I'm going to test this on reasonable text, and parentheses, quotes, dashes pop up in reasonable text, but anything else, yeah, just take it. If a phrase contains 5 spaces in a row, it's 5 spaces in a row, don't worry about it. Right? Don't do anything extra. Even if it makes sense to do something extra. If it's not specified, ask to make sure. So one of the points here is we don't have to change our code that runs off of getCar. We just call our new version of getCar, and we've got this additional pre-processing being done for us. So prompt input parse. So we're not prompting the user for anything here. So we're really just inputting and parsing. But really what we're doing here is we're inputting and we're doing some pre-processing before we parse. Why? To make the parsing easier. So we don't have to worry about is uppercase hello the same phrase as lowercase hello. Right? We're just going to make everything uppercase, and then all these things will look the same. We don't want to worry about sentences being broken up on 2 lines with a new line, right? We want to just treat it as a sentence with a space in the middle. So this is just stuff that's going to make your life easier. And again, the code's not sacred, right? this is probably far more important than the actual code, right? And sort of understanding that this does what you want. I could do this while loop down here at the bottom if I wanted. That would be fine. I could make this whole thing a while loop. I could get a character, go through all of this, and at the bottom I could say, is it a special character I should ignore? And if it is, go back up to the top. There's different ways to slice and dice this, but do what makes sense to you. The other nice thing about this is, you know, how do I test this? Well, I've got a 1, 2, 3, 4, 5, 6 line main program to test it. And I can throw all kinds of things at this. And I don't need to worry about PA4 at this point. I'm just using a little main program to test this getChar function. Well, maybe now I want to develop my function which pulls out a phrase from the input using my getChar function. I can make my getPhrase function, and I can test it the same way. Have a main program that just says get a phrase, print it out. Get a phrase, print it out. Keep doing that until I get to the end of the file.
What if we did if versus while and you ignored for?
Down here at the bottom?
Yeah.
So if these things are true, get a character. Right, so that works great. That not so much. So when it finds the first parenthesis, it calls getChar again, but it doesn't give me a third chance. Right, so the thing that got read the second try gets accepted as a character. The third parenthesis gets rejected and it reads the fourth character, and that's a T, so the T comes through. Good question. All right, any other questions about this or about PA4?
It's part of PA4, right?
Sure.
Got it.
Yeah. And we'll talk probably next week, maybe Friday, about some of these other functions, like how do we pull out a phrase. We can start flowcharting that, but I want you to be working on this on your own first, right? And you should be pretty well into PA4 at this point. Okay, it's almost halfway through the assignment. You should be at a point where you're either building phrases or playing with a dictionary or something along those lines, because time is moving forward as it does.
Are you going to talk about the sorting algorithm and all?
Yeah, I just wrote that on my sheet of paper. We'll talk about that tomorrow. All right, so let's wrap up makefiles, and then I want to talk about file redirection. So here is the makefile that we ended up with yesterday, and a reminder what's going on here, right? Basically, we have pairs of lines which correspond to a target and a command. A target and a command, a target and a command. And the idea is if I say make stick, or if I just say make, it'll look for the first target. If I say make, it'll say I want to make this file called stick. In order to do that, I need these dependencies to be satisfied. In other words, these files up here have to be up to date. And if all those files are up to date, then I will execute this command, and that should make stick. Okay, so how does it know if getUserMove.o is up to date? Well, it looks for a recipe to make getUserMove.o. Here's the recipe down here. It depends on getUserMove.c. And it'll look at the timestamps on those two files. And if the .c file is more recent than the .o, it says, hey, this .o file is stale. I have to remake it. Here's the command for making it. So it'll execute this command, and now getUserMove.o should be up to date. Okay, so it continues. What about main.o? Is that up to date? Well, it'll look at main.o, and if that's more recent than main.c and stick.h, it'll say this is already up to date. Okay, so let's suppose that's the case. Then it'll look at playgame.o. Well, to make playgame.o, it needs playgame.c, stick.h. Suppose stick.h is more recent than playgame.o. Right? This means that stick.h changed, but this has not been recompiled since that changed. And the fact that this is on the same line as playgame.o says playgame.o is affected by stick.h. So it'll say this is not up to date, I need to rebuild it. Here's the command for building it. Once it does that, playgame.o is up to date, and it continues with this and this. Once all 5 of these are up to date, it'll say, okay, I can build stick. All the dependencies are satisfied. Here's the command I'm going to execute. Okay, so let's get rid of stick, and let's get rid of all of our .o files, and let's say make. And it didn't have any of the .o files, so it had to compile all of these .c files, and once it had those .os, it did not have a version of stick, so it executed that last GCC command to build stick. But now if I say make again, everything's up to date. The .o files are more recent than the .c files, so it goes ahead and looks at stick compared to the .o files, and stick is more recent. So I can do ls-lrt to see my files in reverse chronological order, and you can see stick is the most recent file. It's newer than any of the .o files, the make file, or the .c files. Okay, now what happens if I were to change getUserMove.c? We said this will be newer than getUserMove.o, so it should force the make utility to rebuild getUserMove.o, so it'll execute this GCC, and then since getUserMove.o is more recent than stick, it'll execute this big GCC to link everything together. So we can go in and we can edit getUserMove.c and just add a comment or something like that, but when you're playing with this, there's a command called touch, which we can use to update the access time on this file. So if I just say touch getUserMove.c and I do my chronological order, you can see the update time on this is a minute after everything else. So now if I say make, it should say getUserMove.c has been updated. So it'll recompile getUserMove.c. That created a new version of getUserMove.o, and now it had to recompile all of those, link them together to make stick. And if I say make again, everything's up to date. So what if I update stick.h? So stick.h is newer than stick, it's newer than all of my .o files, it's newer than all of my .c files. Well, the way the script was written, stick.h is something that start.o depends on. Why? Because start.c includes stick.h. So if stick.h changes, I need to recompile start.c to get start.o. I also need to recompile main.c, and I need to recompile playgame.c. So if I say make, it should do this, and this, and this. And then once it's got those 3 new objects, it should go ahead and do this to link them all together. So we say make, and like magic, it does exactly the right things. And if I say it again, it tells me it's up to date. So this is the real goal here, is to be able to make a make file for your project. And it's going to be different depending on what your project is, how it's set up. But you can use this as a template. Okay, and I've copied a version over this to the code area that you can get to from Canvas. Nothing wrong with having a make file that you like and just using that and doctoring it up when you want to make a new make file. Right, and for the exam, you know, write out a little tiny make file, put it on your note sheet, and you can do the same thing on an exam. If I ask you to make a make file for a project, start with that and doctor it up. So the real power to a make file is the fact that it captures all of these dependencies. Let me show you a not very good make file. This is not a very good make file. It's one recipe. How do I make stick? Just gcc-o stick all of these .c files. And when I say make, yeah, it builds my executable file make. Here's the thing. If I touch one file like main.c and I say make, it recompiles all of my .c files. Right? So yes, you can say make and it will make your file for you, your executable, but this is not a well-formed make file. This is a really lazy kind of make file. It may as well just be a bash script called make that says gcc-o stick everything.c. Okay? So I want you to be more nuanced than this. I want you to do something that actually honors the structure of your project. Right? In particular, so that if you change one .c file, it doesn't compile all of .c code. Just the .c file that changed and then links the .os together. So play around with that, think about it, ask questions about it, right? Make a directory, just write a main program with 3 or 4 functions that don't do anything particular. You can have a function that just says, you know, I'm function 1, I'm function 2. And try to turn this into a make file for your project, right? But do it on junk code. And once you figure out how to do this once, it's really just the same thing. And I just had a make file that I kept somewhere, and every time I wanted to make a make file, I would just copy that and I just doctor it up. I did that for years before it sunk in, which was only when I started teaching this. Because it's one of those things you do in the beginning of a project and you never think about it again. You just say make, make, make. All right, so let me show you a couple of embellishments we can make to make files. So here's a better version of a make file. So the big difference here is I have these variables called compile flags and ccomp. Ccomp is set to GCC, compile flags is set to nothing. And instead of I just killed my other make file. Instead of saying gcc-o stick blah blah blah, I say $ccomp. This says substitute this with the value of this variable ccomp. So $ccomp gets replaced with gcc. But if I wanted to use a different compiler, instead of changing all of those GCCs to something else, I just change the value of this one variable up here. All right, similarly, I have this thing called compile flags. Right now it's set to nothing. So if I use this make file, and let's get rid of everything in here, and I say make, it just does gcc-c, gcc-o. Now suppose you want to turn on debugging, right? Really, to do that, what I need to do is everywhere that I say GCC, I need to change that to GCC-G. And I do that 1, 2, 3, 4, 5, 6 different spots in my make file. If your make file is like 500 lines long, that's a lot of editing to do. And you never want to like break a make file because they're really hard to read. So I have this thing called compile flags. And if I just set this variable equal to -g, and I say make again, now it says GCC-G. So now it's compiling everything with the debug flag turned on. And if I wanted to turn on array bounds checking or buffer overrun protection or turn on profiling or turn off something and so on, I can just change my compile flags. And I don't have to actually edit the bulk of the make file. So that's one thing we can do. We can add these flags, these variables, and make the script more general. And it's kind of like using a define, right? So you don't embed magic numbers. The other thing I've done here is I've added a new target down here which is called clean. And this is kind of a trick. So if I say make, it looks for the first target which is stick, and it tries to make stick. if I say make main.o, it will look for a recipe for main.o and it will try to build main.o. So main.o says I need main.c stick.h, and then I have to compile main.c with a C flag, which is what it just did. If you say make blah, it'll look for a target name blah. Okay, so what happens if I say make clean? It will look for a target name clean. It finds one right here. There's no dependencies that have to be satisfied. So it says, okay, I'm all set to go. I can make clean. Here's the command that I've been told I should execute to make clean. Well, it doesn't make anything. It doesn't compile anything. It actually removes some stuff. It removes those .o files in the executable stick. That command that I keep typing every time I want to show you something new with the make file. So I can trick this utility into removing those files by just saying make clean. Now why would I want to do that?
To recompile it.
To recompile it, because maybe somebody wrote this code on their system and they compiled it and they linked it and they've got the executable and they pushed everything over to Git, including all of the .o files and the executable. And I download that onto my Raspberry Pi, and I know I have to recompile everything to make it run on my Pi, but if I say make, it's going to look at the dates and say stick is up to date. So now I got to go in manual and I got to find all the files that I'm supposed to delete, right? So it's kind of a convention to include a clean option that basically gets rid of everything if you want to force a full recompile. So if I say make, it tells me everything is up to date. If I say make clean, that gets rid of stuff, and now if I say make, it redoes all of those compiles. And we can do this more generally, right? We don't have to have things that call GCC. We don't have to have things that have anything to do with compilation or linking or anything else. We can put anything in here that we want. So here's a really kind of annoying one, but just to sort of push the point. Right, so there's a target called me laugh, and it has no dependencies, and the instruction to make me laugh is echo ha ha ha.
I get it.
Right, get it?
I'm so dumb. Why is that so
Yeah,
funny?
I know. So, but you can do whatever you want with the make file, right? And this is actually really useful for a variety of things. So text processing has long been a part of Linux environment, going back to like the 70s. Some of the early work with tech and stuff. Early days of computing, right? Academics were using Linux for a long time. And the first computer networks were really established by academics for sharing information on research they were doing. And you know, you write a paper and you publish it, but before you publish it, you've got to have people look at it and review it and stuff like that. A lot of the early networking stuff that was set up was done to promote peer review among physicists, largely, mathematicians, other scientists. And there were systems developed, tech was an early one, for doing text processing, for making really beautiful documents that included things like mathematical formulas or you know, things like that that don't fit in like just a plain old email message. And so you can make a make file to create your document, because to create your document you have a file containing your text, you might have another file containing your bibliographic information, you might have another file containing information about the figures that you have, and there's a series of Unix commands that you use to put all of that together into, you know, today maybe a PDF or something. And you always have to run the same 12 commands, right? But if you change the bibliography, you've got to run this other set of commands. If you add a new figure, you've got to run this other set of commands. You can put all that in a make file. And every time that you change your text, you just say make, and the PDF pops out, and it's updated. And some of these documents, you know, trying to process them every single time you make a change takes a long time. It might take 5 minutes to rebuild all of the documents. And if all you've done is change one bibliography caption, right, maybe you don't need to rebuild everything. So make files get used all kinds of different places. It's a very general utility. And so it's a good one to have in your repertoire. So you'll probably see a make file question on the final, so play around with them, make peace with them. All right, any questions about this? So this is the version that's posted on the server that you can get to through Canvas, but it doesn't have to be fancy with the variables and stuff, but do more than just compile all the .c files. All right, so we've talked about input redirection. If you have a command that normally reads from standard in, you can have it read from a file instead of standard in by saying command less than and the name of the file. And we've been doing this with our Go program. Right, so Go reads from standard in. If I say Go less than the name of a file, it reads from that file instead. So it changes where standard in comes from. We can also do output redirection. So if we say command greater than file, then standard out, instead of going to our display, will be sent into a file. So if I say cow say this is fun, that command displays this on my screen. My standard out is connected to my display. If I say cow say this is fun greater than cow file, instead of showing standard out on my display, it's sent standard out into this file called cow file. And if I edit that file, it's got the output of cow say. So now I've got a file with talking cow in it, which I could put in my comment block of my program if I wanted. If I say ls-l, that shows me all the files in my directory. If I say ls-l greater than out, I don't see it on my display. Where did that output go? It went into a file called out. And if I do an ls, now I have a file called out. And if I look inside that, it's got the results of ls-l.
What is an existing file?
It depends on your setup. So I should be set up to just clobber it. But you can set up variables in bash that'll tell you that file already exists, and then you have to force it to write. And if you do two greater than signs, that says append. So ls-l shows me that. If I say ls-l greater than cow file, now if I look at cow file, it's got the original contents, which was my talking cow, followed by the results of ls-l. So you can append things to your output. And this is a nice way to capture output, especially if your program is spewing, a bunch of stuff on the screen and you don't want to go back and scroll through it and so on and so forth. Just greater than it out to a file, and now you can edit the file and you can move around and search for things and stuff like that. So I just broke my go.c function by getting rid of my prototype, and when I try to compile, I get an error message. And suppose that there were 5,000 error messages and I wanted to be able to read those in the file, I might try doing this. gcc-o go.c greater than errors, but the output still comes up on my screen, and if I look at my errors file, it's totally empty. Okay, this is really redirecting what we call standard out, and this is redirecting what we call standard in. So standard in is your keyboard, standard out is your display. There's another output channel that we can use, which is called standard error. And when GCC has an error to report or a warning, it doesn't actually send it to standard out, it sends it to standard error. And so if we want to redirect standard error, we can say greater than ampersand, with no space between them. So if I do this, greater than ampersand errors, now the output that GCC produced went into my file, and I can edit that file and I can see what the error message was and so on. So there's one input, standard in, there's two outputs, standard out and standard error. Alright, so I can take my steam locomotive and put that into haha. And that's what SL does when you type it in. It produces all of this output. Those blue control left brackets, those are escape characters, ASCII code 27. And if I cat this, it will show you my steam locomotive, but really, really, really fast. Right, so normally it's produced with a delay so that you can actually see it, but it's going too fast to see. But when you do the SL command, it comes out slowly. All right, so we'll talk a little more about input-output redirection tomorrow. We'll talk about bubble sorts and review that for PA4, and then we'll go on to something new. Hey, Rick.